Physics 40S. For once, I'm actually going to be on camera for this because I wanted to demonstrate. We have a model of an electric generator. I know hopefully you've already watched the video that we asked you to watch on electric generators, but I found that it was a little bit confusing for the hand rules. So I wanted to use our model to help you out a little bit. So we have the external magnetic field, north and south. So we would have field lines coming in this direction. We have an armature, which is the coil of wire. This is obviously not wire, this is PVC pipe, but it represents the wire, and it's only one loop where it would be hundreds of loops usually. Then we have here, made out of paper, so not very realistic. We have a slip ring here, and then a second slip ring below, and then we have the brushes that are all parts. So those four things are the important parts of the generator. We have the external magnetic field, the armature, the slip rings, and the brushes. Now, one of the things in the video that you may have noticed is during the rotation, we're trying to track the induced EMF. So part of a generator is we put mechanical energy in and we get electrical energy out. Well, how does that happen? We know that we are rotating. There's a crank up on top that I could turn, but I'm going to just push on the armature, which is not really how it would happen, but we're going to pretend. I'm going to take a velocity vector V, and let's say I'm going to rotate and put this side of the armature is going to be going into the page, although this is not page, and this side would be coming out as I'm rotating. So if I was turning up there, whether it was water or wind that was rotating this armature, any of those things could be happening, but this is rotating in a magnetic field. Now what you'll notice, the velocity is going this way, the magnetic field was coming in this direction. So I could have a little arrow showing the magnetic field going that way. Yes, I know B's upside down, but that's okay. So we have the magnetic field going in this direction, velocity going that way. Hey, we have a bunch of electrons sitting in here and they're moving in a magnetic field. So that means they're going to have some kind of a force exerted on them. And luckily, we have a hand rule that explains this. So if I take my thumb and use that as the velocity direction, the rest of my fingers point in the direction of the magnetic field, my palm is facing downwards, which means that there's going to be an EMF or a force. Okay, a force, this is the force, so it's going to push down. That would cause those positives to move, even though we know positives don't move. And the positives would create, a net positive down here and a net negative up here. Now we might choose to say, okay, then what's going on with the charge? And we could find the direction of the flow of the charge in the rest of the coil. But the problem is we're looking at just this little section. So I'm going to use this here to represent the direction of the force. So there's a vector arrow here. It says I on it. You're going to get upset about that, I know, but we're just going to pretend right now. So then we have a downwards force. So let's pretend that was an F. Now what's happening over here at the same time? This side is coming out of the page. So my thumb is going to indicate the direction of the velocity. My fingers go from north to south. My palm is facing upwards. So that means we're going to have a force that's exerted on those protons, indicating this direction. So we end up with, you'll notice, two opposite directions on the two sides of the coil, but in combination, we can create a continuous path. Now you'll notice this section right here is not really moving relative to the magnetic field. So that means there's nothing induced in here. But if we have those forces exerted on the charges, it's possible that they will feel the electric field and they will move in conjunction with those other two forces. Now great, we've created EMF, but how do we get it out of there? That's the purpose of the slip rings. You'll notice this current, if we're going to call it current now, would flow down here, come in through this yellow connection, down to this slip ring, and then out through this brush into an external circuit. it would come all the way around in through this brush and up and over and make a complete circuit. Okay, so we would get current in the external load, removing the energy that we've created there. Now, as this rotates, you'll notice now that the velocity is happening parallel to the magnetic field. So now, what's the angle between those two things? It's 0 degrees. What happens when we have the sign of 0? That's also 0. So we have no current induced when we're at that location in our rotation. So we have a 0 current created. Okay, so we had maximum here because we were 90 degrees from the magnetic field, 0. And then notice as we continue another 90 degrees of rotation, here, look what's going on now. Velocity's going in this direction. Magnetic field's coming this way. I'm going to get current induced here and current induced here. Okay, so we end up with, again, maximum current. Now, something strange has happened though. This current is now going to go in through the white slip ring. They're not really white and yellow, it's just paper I had. And it's going to go in through the white slip ring, out through the external brush, which doesn't want to stay in place no matter what I do here, and then come around, go in through the yellow, and up and around. So if you notice, it reversed direction in the external load. So outside here, we came out and around this way, whereas previously we were going in the opposite direction. So we create something called alternating current. If we want to graph the voltage that's created, we started at a maximum value, then we had 0, now we have the opposite direction. What do you think is going to happen when I rotate another 90 degrees? Take these off. We're moving parallel again. So we're back to 0. And then we would be back to maximum, and you'll see we've created like a cosine curve. Not very well drawn, but don't tell the math teachers. Okay, so we see that there's a cosine function or a sinusoidal function. If I look at the adjustment that would happen, this would be a sine wave as well. So that's the end of the generator. Stay tuned for motors.